Assalamualaikum and a very good evening. My name is Nofazana binti Muhammad Zakaria, mentor ID A202580. I will briefly explain the objective and problem statement of this project. The objective of this project is to study the feasibility of using supercapacitors for ultra-fast smartphone charging, potentially within 10 seconds. This includes understanding their energy storage, rapid charge-discharge behavior, and comparing their performance with lithium-ion batteries in terms of charging speed and efficiency. However, the increasing demand for faster charging highlights the limitation of lithium-ion batteries, such as long charging times, heat generation, and reduced performance. Although supercapacitors offer fast charging and long cycle life, their lower energy storage presents challenges. This project evaluates whether supercapacitors can realistically support 10-second smartphone charging while maintaining safety and efficiency.
At the fundamental level, energy storage is a trade-off between speed and capacity. Today, we're comparing the electrostatic storage of capacitors against the electrochemical storage of batteries. Capacitors rely on the electrical double-layer phenomenon. They store charge physically on the surface of electrodes using a molecular dielectric. Because no chemical bonds are broken, the process is nearly instantaneous and highly efficient, reaching over 98% round-trip efficiency. Batteries, however, utilize chemical potential. Energy is stored within the atomic bonds of the anode and cathode. While this chemical process is slower, it allows for incredible energy density. In fact, a lithium-ion battery can hold 65 times more energy by volume than a standard supercapacitor. Longevity is where they diverge most. Batteries suffer from cyclic stress and SEI layer growth, which eventually degrades the cell. Capacitors undergo minimal physical change, surviving millions of cycles.
I will explain about why does graphene allow us to store so much more than a normal capacitor. First, we need to know standard capacitance formula, which is capacitance equal to permittivity times surface area over separation distance. Graphene has small separation distance. This separation distance for graphene is approximately 0.4 nanometer. This is because graphene is perfectly flat at atomic scale compared to traditional metal electrodes. Secondly, graphene has a large surface area. Single-layer graphene has a high surface area due to its two-dimensional nature, which is one atom thick. Theoretical calculation show that the specific surface area of graphene sheet is approximately 2,630 meters square per gram. Lastly, graphene has high permittivity. Graphene can achieve high permittivity value. For example, the permittivity of reduced graphene oxide is 1,130 farad per meter at 50 Hz.
So now I'm presenting the hybrid car proposal. The first is handling high current versus ESR optimization. So battery have high internal resistance which cause heat and stress during massive power draws, like starting a car. So by having a supercapacitor have resistance that is 10 times lower, that acts as a shield handling these high stress cracking events so the battery doesn't have to. And the second one is efficiency in regenerative braking energy recovery. So during braking, a vehicle generates a massive energy spike in a very narrow windows of 3 to 5 seconds. So the research indicates that supercapacitors are significantly more efficiency at catching this energy, recovering up to 53%. So energy more than a battery alone. And the third one is the cycle life and system durability. A lithium-ion battery survives roughly 3,000 cycles. How about a supercapacitor? It's about 1 million. So by letting the supercapacitor handle the millions of stop and go cycles in city driving, we keep the battery stable, extending its total lifespan by up to 50%. So in conclusion, in short, this hybrid car approach maximize efficiency, protect the batteries, and significantly lower long-term costs. Thank you.
Capacitors are likely same as humans. As while they're young, they are very active, and starting to get old, they lose their capacitance and the internal structure starts to degrade over time. So let's move on to the main scenarios that might occur in electrolytic capacitors. Firstly, is water droplets. Water droplets from the surrounding environment penetrate the capacitor and causes rusting to the metallized electrode layers, and this weakens the capacitance tolerance. Next, electrolytic capacitors, mainly in the battery and the charger of the phone, has poor isolation resistance, making it more current leakage, which unable to isolate charge properly, allowing some of the current to escape. And for the final, capacitors may lose some of their capacity when left unused. That's all. Thank you.